to everybody that I registered and have the link. Hi, Shweta. Could you please rename yourself? I will appreciate that. Too many Zamans might create some confusion. I registered and have the link. Wonderful. Wonderful.
Looks like I'm in the multiverse of Marvel right now. So many Spider-Man around.
Hi, Angelina.
Hi, Elena. Good to see you.
I'm going to just give you a floor for a few minutes, Angelina. You can just introduce yourself. I'm just waiting to join a few more people. Then I'm going to start. It's 6:32. Let's see. I'm expecting a few more people to join. So, folks, those who joined in this Zoom session and my name is popped up instead yours means you're using my link. I will appreciate if you could rename yourself.
Okay, so we are live on YouTube.
Okay, wonderful, wonderful.
And when you give me the go ahead, I will start the recording on the cloud as well.
Sure, yeah. All right, so I'm going to start the session now formally. Hello, everyone. Welcome to tonight's session. Vishnu, if you like to record, you are welcome to record now.
Yeah.
Thank you so much for joining this special event. And the title of today's seminar is Unveiling the Transformative Power of Unsupervised Machine Learning through Clustering. So clustering through machine learning, that's today's theme. And I'd like to welcome today's speaker, Dr. Vishnu Pendalia. He is a faculty member at San Jose. He's a faculty member in the Department of Data Science, Applied Data Science, and Santa Clara Valley. No, it's San Jose State University, and he's also the chair for Santa Clara Valley chapters for IEEE Computer and Computational Science. Dr. Pendalia also a distinguished speaker for IEEE Computer Society. So he's a well-known academic and researcher. So thank you so much, Dr. Pendalia, for accepting our invitation and agreed to become the speaker for tonight's session. So this event is co-hosted by Kitchener. The primary host of this tonight's session is primarily hosted by Kitchener-Waterloo section, chapter Computer Society, and Conestoga student branch for Conestoga College, along with Santa Clara Valley section chapter and Santa Clara Valley section student chapter. So welcome everyone. We are going to start in a minute. We can see Angelina Gismar. She is the chair for Conestoga College student chapter, IEEE KW. I like to welcome Angelina and all others. We also have a faculty member here, Sweta Gupta. Thank you, Sweta, for joining. So Angelina, could you please introduce yourself briefly as a co-host of tonight's session and as a chair for student chapter for Kitchener-Waterloo section, IEEE. Thank you. Angelina, we can't hear you. Probably you're mute or something. Okay, so there is a sound glitch. That's no problem. Thank you, Angelina, for joining here. We have some difficulty hearing you, but So,
think,
Dr. Vishnu Pandalia, welcome. And now floor is yours. Please start your presentation. But I have a request. After an hour, if we could take a short question and answer session, then some people could might ask you some question before leaving. So if someone need to leave after hour and a half, feel free to leave the session, no problem. This session will be long and will be around 3 hours. Thank you. So Dr. Pandalia, floor is yours. Please go ahead and start your presentation.
yeah, thank you, Zaman, and hello, everyone. Please feel free to post your questions in the chat window, even during the first 1 hour. And whenever I get a chance, I'll try to answer the questions. So today's topic is the transformative power of unsupervised machine learning through clustering. To give you an analogy, children grow up supervised with their parents labeling everything for them. The children are told what is good, what is bad, do this, don't do that, etc. And then time flies and children turn 18 years old and start discovering life unsupervised. So there are no longer labels. So they have to discover the labels themselves. So the first thing they try to do, unsupervised, is to form groups of friends, right? Now that there's no supervision, there's no oversight from the parents, they like to choose the friends that they want to be with. And how do they choose the friends? It is usually by the features of the people around them, right? Typically latent features, latent characteristics. So that's what we do in machine learning as well. So the supervised machine learning is all about data with labels, and unsupervised machine learning is about data without any labels. So we try to recognize the characteristics of samples. Another analogy is why are rice, wheat, potato, taro root, and similar kind of food items staple food? So if you have gone to Hawaii, for instance, the staple food is taro root. If you come to United States, the staple food is potato. North India, it's wheat. South India, it's rice. So what is the reason that these are the staple food? So the reason is there's a hidden factor in all these food items, and that is the carbohydrate. The rich content of carbohydrate is what is common feature across all these items. So similarity is not apparent. It is often hidden. And so grouping or clustering is all about discussing these latent features to group things together.
I'm sorry to interrupt you. Okay, the slide is changing now. Thank you.
Sorry, Vishnu, I think you are on mute, so we couldn't hear you.
Oh, I don't know how that
Yeah,
happened.
we can now. Sorry.
Okay. So another analogy is how do streaming services know that these movies can be grouped? So you see a lot of movies on the slide like Ben-Hur, Last Samurai, Bahubali, The Last Emperor, and things like that. So how do the streaming services know that if you have watched Ben-Hur to suggest Gladiator, for instance? So it is again based on similarity of features of various items, right? The more powerful algorithms try to discover the latent features and then discover the similarities across those latent features. So in the case of these movies, the hidden features are machoism, battles, dynasty, monarchy, and things like that. Sometimes these features may not be explicitly given. We need to discover these features. So that is the goal of unsupervised machine learning typically. So just like a prism, in science we have studied about prisms. Prism is used to discover the latent spectrum of white light. There are ways to bring out the spectrum of given data. So that's the reason why in machine learning these are called spectral methods. Um, uh, for instance, if the data is in the form of a matrix, a simple spectral method is to compute its eigenvectors, right? So that is typically done for recommender systems. The question here on the slide is features. So it is based on the features that these movies are grouped together. So features are expressed as vectors. So you take a movie like Braveheart and you extract features from the movie. The features could be a rating for the genre, genre action, genre drama, war, and things like that. So give values for each of these genres. And then you come up with this feature vector. So the vector is written typically like this in a transposed way. But as you can see, there are no labels. So we need to do things without any labels. Some useful things, generate value from this data without any labels. So just like for human beings, clustering is one of the commonest forms of unsupervised learning. Like we talked about the children forming groups, unsupervised. So same thing happens here. So this is a popularly known clustering application. So there are 4 features here. The first feature is the number of arrests per 100,000 residents for assault, murder, and rape. And so those are the 3 features. So and the 4th feature is the urban population in each of the 50 United States in the 1973, in the year 1973. So, so we have a data set there. The 4 columns are, like we mentioned, number of arrests per 100,000 residents for assault, for murder, and for rape. And the 4th feature is urban population. So all we can do is compute distances, but these distances are not physical distances, but distances across features. So obviously there is a purpose for doing this. We want to group the states with similar kind of arrest records together. So as you can see, states which are far away are also grouped together, right? Like for instance, you see Virginia and Oregon, for instance, are grouped together, right, in the same group. Similarly, Arkansas and where else? Mississippi are grouped together. So it does not depend on the physical distance, but it is dependent on these 4 features that that I mentioned earlier. So as can be seen here, clustering is popularly used for segmentation. So in this case, it is a segmentation of states, but sometimes it is a segmentation of the market. Sometimes it's a segmentation of images, social media users, and so on and so forth. So why do we segment all these things? It is basically to divide and rule, right? Whether it is in software or real world, we often divide to rule. So clustering relies on distances in the feature space. So these distances may not correspond to the physical distance like we saw in the case on the slide. So distance is used as a measure for similarity. So the smaller the distance, the better the similarity, right? So that is the idea. So if the features are all similar, then the distance between the feature vectors will be small, right? From the vector algebra that we learned from the high school, we can confirm this. So the goal of any clustering algorithm should be to maximize the distance between clusters. So the distance between this orange cluster and the blue cluster must be as maximum as possible. Between orange and yellow should be maximum as possible, and things like that. The other goal is to minimize the intra-cluster distances. That means the distances between the items in a single cluster must be as minimum as possible. For instance, South Dakota is very similar to Montana in terms of the arrest records, right, in this example. And there are no labels. It's unsupervised. The machine learning proceeds in an unsupervised way. Supervision is pretty expensive, right? I mean, parents getting supervision from parents is a blessing, actually. It's not easy to get supervision from well-wishers. Unfortunately, it's not fully understood these days, but supervision is expensive, and we are fortunate if we can get supervision. So if there is supervision, there are labels, and if there are labels, the process is called classification. But here we are concerned about unsupervised learning, therefore it's called clustering. So there are many applications of clustering. So one big application is in social media. So I deliberately blurred these screenshots, but to preserve the identities of the people featured in this. But you would have seen similar kind of screenshots when you open social media websites. Like the social media websites could be suggesting similar profiles, or they could be suggesting people you may know, and things like that, right? So that is one big application of clustering. And the other application is in information retrieval, right? So this is a screenshot from Google Scholar. When you search for DBSCAN clustering, for instance, the Google Scholar webpage also shows related articles. So how does it know what are all the related articles? It's by doing something like clustering, right? But the clustering is for documents here in this case. You can also see applications online for image clustering. For instance, when you go to Google Images and search for dog, you first see the dogs classified into subcategories. Like you could search for puppies, you could search for dogs which are drawings, you could search for dogs which are clip art, or you could search for breeds like Labrador, right? So that is the high level of clustering. And you can go further. If you select drawing, then you can Google groups them into easy drawings, cute drawings, pencil drawings, puppy drawings, and so on. And you can choose further cute drawings. And now the clustering happens based on the cute dogs. So clustering is pretty much there everywhere. So what is the difference between classes and clusterings or clusters, right? So classes are defined and data labeled manually. So the definition of classes happens manually in a supervised fashion. So this is a costly process, particularly if the data runs into several billions of items, then it's going to be really expensive to do the supervision. Whereas clusters, on the other hand, are automatically deduced. So there are no labels. We just group the items based on their features. So what are some of the hyperparameters that you can choose for clustering data? So hyperparameters are the parameters or the fine-tuning parameters that human beings choose. So the first parameter is the similarity metric. Like, how do you measure similarity? So we thought that distance is the way to measure similarity, but there are many kinds of distances. So some of the metrics could be cosine similarity, Euclidean distance, Manhattan distance. There's also something called geodesic distance. We'll look at each of these distances very briefly later. So that's the first hyperparameter. And the next hyperparameter is the type of clustering. So the clustering that we want to do could be partitioning, like forming non-overlapping subsets, or it could be hierarchical, like so creating tree-like structures from the data. It could be based on density, or it could be fuzzy clustering. So this type of clustering is borrowed from the fuzzy logic, uses concepts from the fuzzy logic, where the points, data items, can belong to multiple clusters with varying degrees of membership. So there are many types of clustering. I just listed a few, but there are many types of clustering. So you'll have to choose a type of clustering that is best for your application. And then once you decide on the type of clustering, the next thing to do is to determine the algorithm that you want to use for doing the clustering. So there are algorithms like k-means. For hierarchical clustering, there is agglomerative clustering algorithm, or you could use a divisive clustering for hierarchical. And then for density based, you can use DBSCAN. So these are some of the algorithms we are going to cover today. And for some of these algorithms, the third or the fourth hyperparameter that you need to choose is the number of clusters. So some algorithms like k-means need this value for the number of clusters, which is all these hyperparameters they're not easy to decide. You need a lot of intuition to decide on each of these hyperparameters. And that is typical of any machine learning algorithms. Most machine learning algorithms have hyperparameters, and deciding them is quite a bit of a challenge. So for many data sets, the number of clusters is very apparent, right? So typically in binary classification kind of problems, the number of clusters is just 2. A lot of data sets are binary in nature. So we want to just determine one class or the other. So typically the value of the number of clusters is just 2. And for some other data sets, we know the value of the number of clusters based on the data set itself. For instance, handwritten digits. Suppose there's a data set for handwritten digits. How many classes are there in this kind of a digit data set? 10, right? So 0 to 9. So there are handwritten digits which can be categorized into 10 groups. But for most others, we need to determine ourselves. So before we get into hyperparameters, let us generally consider the problem. So how can we detect and form these clusters of data points shown on the screen programmatically? Machines don't have eyes. We can look at the screen and say, okay, there are like 1, 2, 3, 4 clusters, and we can draw circles around them. But machines, we have to provide the vision to the machines. We have to program the machines to see these patterns. So how do we do that? So that is the problem we are going to solve in today's session, right? So to understand these algorithms, the approach is to form these kind of clusters. Let us see how we form clusters in the real world. Like in our day-to-day lives, we see a lot of clusters. So one big example is that of the political parties. How are clusters formed in political parties? Or how are political parties formed? So typically there is a visionary. This visionary is the most representative of one kind of ideology, right? So for instance, this ideology is all about being liberal to the citizens, right? giving them what they need and taking care of them very well and things like that. So that is one ideology, and this person has that ideology and is quite representative of that ideology. Similarly, there's another person who is representative of a second ideology. This ideology could be more conservative, like the value system is very conservative, and preserving the value system is what this person is focused on. Then the people, both of them start spreading their ideas, and then people start joining their teams. So the people on the left you see are closer to P1 than to P2 in terms of ideology. So all these people believe in liberal values. Whereas some other people, based on the second person's speeches and things like that, they become closer to the second ideology, the conservative ideology. So these people on the right-hand side are closer to P2 than to P1 in terms of ideology. So that is the idea behind an algorithm called k-means. So here the value of k is 2, just 2 clusters, but k could be any number. So that is the first algorithm that we are going to talk. But let us look at how else clusters are formed. So another great example for clusters is the neighborhoods, physical neighborhoods, right? So typically in most cities, but I mean these days everywhere probably, there are communities of homes, right? Like there could be a community called ABC on the left-hand side, and another community called XYZ on the right-hand side of a street, right? So how are communities formed? It is based on the density. So if you can see, the houses are all densely populated in one area on the left and another area on the right. So here there is no representative point. We don't really care who or what is the representative house and things like that. We just group the clusters based on density. So the closer the homes are, they form a cluster. So that is the idea behind an algorithm called DBSCAN. So that's the second algorithm we are going to cover in today's session. And then there is another natural way of clustering things, and that is called hierarchical. If you have studied botany or zoology, you would have seen a lot of such hierarchical clusterings, taxonomies of biological species. So bacteria, archaea, and eukarya are three constituent forms of life. These are the major groups of life forms. So archaea are often similar to bacteria in size and shape, but they are different. And eukarya are organisms whose cells have a membrane-bound nucleus. And unicellular organisms are eukaryotes, as they are called. So as you can see, bacteria, archaea, and eukarya, they are further subdivided into subcategories and things like that. So basically, we form a taxonomy of life forms using this idea of hierarchical clustering. So this is the third clustering algorithm we are going to cover in today's class, all based on data, right? We collect a bunch of features from a bunch of samples. We create a table and start clustering. So these are the three clustering algorithms for today: k-means, hierarchical clustering, and density-based spatial clustering of applications with noise, abbreviated as DBSCAN. So once again, the goal of clustering is that the entities across clusters must be as dissimilar in the feature space as possible. And within clusters, the entities must be as similar in this feature space as possible. So why do we call feature space? It is because, remember, we extract features in the form of vectors. And what is a vector in linear algebra? So vector, there are multiple ways to think of vectors. One of the popular ways is, of course, like a single dimensional matrix like this. But the other way to think of vector is as a point with magnitude and direction. So this vector 8, 7, 6, and so on can be represented as a point in a space, vector space, with magnitude and direction. So each of the elements are the values across the dimensions. So the first dimension, the value is 8. The second dimension, the value is 7, so on and so forth. So we plot a point across all these dimensions with these values. And so that's the movie Braveheart becomes a point in that vector space. So that is the reason why we keep saying feature space. We use feature space again and again. So the idea is to form clusters which are as far apart as possible. So the distances across clusters must be as maximum as possible, and within the clusters must be as minimum as possible. So that is the idea. So the first algorithm we are going to cover is k-means clustering. So to develop the intuition for k-means, let us consider the example of school districts. So I'm pretty sure in Canada as well, you have school districts, right? The cities or the counties are divided into, for instance, in this case, we are looking at the school districts in North Carolina state. So North Carolina is in the east coast of United States. And this is how they came up with the school districts in the state. So there are 1, 2, 3, 4, 5, 6 school districts, or maybe 7 school districts. And these 7 school districts were formed based on the proximity to the schools, right? So the goal is to minimize the distance from the homes in the same district to the school. And of course, the distance from the school in a different district must be as high as possible. So that is the idea, right? So the distance of homes within a school district should be close enough or should be small enough, and the distance from the homes in another school district should be far to justify multiple clusters. So the school can be thought of as a centroid. Like, you know the meaning of a centroid, right? Centroid is like a center, right? If there's just one, for instance, let us consider just one high school. So per district, that is, it would be really unfortunate if we have just one high school, but just for a moment, let us think that there's just one high school for the entire district. So that school is kind of like the centroid, geometric centroid of this entire area. So how do you determine centroids? It's based on taking the averages, right? So that is the reason why this algorithm is called means. We take averages. So we'll talk about centroids in a couple of slides from now, but so that is the central idea. So there are K clusters, and each of these clusters is represented by a centroid, which is like the mean of the vectors. So that is the idea of k-means. That is the intuition behind k-means. So let us look at the algorithm using an animation. So I came across this nice website with very cool animations for all the clusters. Oh, this is not extending. No. Okay, good. So how do you pick the initial centroids? Let's say randomly. And we want to determine Gaussian mixture. Let us do a Gaussian mixture. So there are 3 classes, visible classes or clusters in the data set. So what we do is we first choose the centroids randomly. So here the centroids are chosen randomly at different places. And then oh, sorry, this is the first centroid here. And we add another centroid. So this second centroid is also in the same cluster as the first centroid. Why? Because we are choosing the centroids randomly, right? So, and then there is a third cluster. Okay, let us think that there are just two clusters. In reality, there are three, but let us see what happens if we choose two clusters. So we click on two, and so as you can see, some clusters are already formed. Now, based on the clusters, so the orange area is one cluster and the blue area is the other cluster. So the centroids are now going inwards to the clusters. Why? Because in the previous case, they were not the true centroids, they were randomly chosen. So now these are true centroids for the points in the clusters. So there are some points here, there are some points here. So the centroid is midway between the points, the vectors, the feature vectors, right? Similarly, the same thing for the red features. So then we keep doing this again and again. Update centroids, reassign points, update centroids, reassign points, update centroids, reassign points. Now the centroids do not change, and the points, the decision boundary also does not change. So that means the algorithm converged, and we have two clusters now. So the algorithm successfully found two clusters, but we can start it to form three clusters. So once again, there are three clusters, but because the centroids are chosen randomly, they are not really ideal centroids for the clusters. So we keep doing this: update centroids, reassign points, update centroids, reassign points, and that's it. In a few steps, it converges. So it doesn't change. The clusters do not change anymore, how many ever times I click. So that is the algorithm. That's it. Very simple algorithm. So these regions that k-means algorithm finds are typically called Voronoi diagrams. In case you are familiar with topology, these are called Voronoi diagrams. These kind of spaces which are divided. But anyway, that's not too important. What is important is the key ideas in k-means. So the first idea is that of a centroid. So what is a centroid? If you remember from middle school or something, the centroid of a triangle with coordinates x1, y1, x2, y2, x3, y3 is given by the average of x1, x2, x3 and y1, y2, y3, right? So that is typically denoted by mu, which stands for mean, right? You can abbreviate this notation as mu is equal to 1 by 3 sigma xi and sigma xy, yi. So that is the idea of a centroid for triangle. You can extend the same thing to data points. So data points are vectors. So in this case, in the case of triangle, the coordinates are also vectors. The only difference is these vectors have only two elements, but our vectors can have any number of elements, thousands of elements, right? So let us consider m data points. So this is the first data point with n number of dimensions in the vector x11, x12, so on till x1n. This is the second vector. So what do these represent? These points represent, these are feature vectors for samples. So the samples could be people, they could be students, they could be anything, right? So these are the feature or the movies that we talked in the beginning of the session. So these are all points in the vector space with all these features. So they are m data points. Now, what is the centroid for these points, m data points? It is again the average. So 1 by m times the same thing, the same summation of the elements. So this can be abbreviated and written as mu c, the vector mu c. So remember, the mean is also a vector of the same number of dimensions. So vector mu c is given as equal to 1 by the number of points in the cluster, which is represented by modulus operator of C, cluster C, summed by the vectors in the cluster. So that is the idea of a mean of points in a cluster. Okay, the next important concept in clustering algorithms is the similarity metric. So there are many similarity metrics in use for various applications. So the first is the Euclidean distance, the simple Euclidean distance that we typically compute in geometry, like coordinate geometry, right? Xi minus yi squared. If in two-dimensional case, you just have n is equal to 2. But if there are thousands of dimensions, n could be anything, right? And the properties are that this notion of distance is very intuitive. We are very familiar with this kind of distance. It preserves the original space. So you don't have to come up with a new space. The distance is as measured in the original space. And it is best used for continuous data and low dimensional spaces. But the limitations are that it is very sensitive to outliers. Why is it sensitive to outliers? Because we are taking a square. So if the point is somewhere away, because of the squaring, the difference, the magnitude of the difference becomes really great. So for small distances, because we are squaring, the distances get amplified. So that is the reason why it is sensitive to outliers. Outliers are important when doing clustering, right? So for instance, as an example, suppose we talked about these clusters. What if this house wants to be totally different, right? In terms of features of the homes, if this home wants to be totally different, it could be a problem for clustering, right? In terms of features. So so that is the reason why typically in the homeowners associations of communities mandate that the homes all look very similar, so that they can belong to the same group. Similarly, in case of political parties, what if one person does not align as much as the other people in the party, right? So that can cause problems. So outliers are always a problem, are a different type of issue. So that's the reason why you need to consider the sensitiveness to outliers when you consider the distances as well. And then because this is squaring, it struggles with high dimensions. So that is one problem. A simplified distance is Manhattan distance, where you just take the absolute difference across each dimension and sum them up. So that way, because we are not squaring, it is less sensitive to outliers. It is computationally very efficient because you are not squaring it. And it is particularly helpful when the problems require grid-like paths, right? The problem is that it is less intuitive. You have to keep going to Manhattan to understand how Manhattan distance works. I'm just kidding. Manhattan or any downtown, for that matter, has similar kind of distances, right? So it is less intuitive. It may not capture diagonal relationships, obviously because we are going in along the dimensions. So it does not capture diagonal relationships. And then there is a generalized form of both the Euclidean distance and Manhattan distance. It is called Minkowski distance. So for various values of p, you can reproduce different distances. For instance, when p is equal to 1, it becomes a Manhattan distance. When p is equal to 2, it becomes a Euclidean distance. So therefore, it generalizes both the distances. It is particularly useful when the optimal parameter, optimal distance metric is unknown. So we can play with different values of p. But the problem is it's a double-edged sword. The problem is that it's choosing p is a very big problem in itself. So that is a problem with Minkowski distance. Then there is cosine similarity, which is very commonly used in machine learning and information retrieval. It measures the angle and not magnitude. It is very widely used in text analysis, text mining, recommender systems, and particularly when direction matters more than magnitude. But the limitations are that it's not a true distance metric. For a metric to be a distance, it should satisfy triangle inequality, right? So if you have studied the idea of metric spaces, you would know about triangle inequality, right? Like for instance, in Euclidean geometry, triangle inequality, what is triangle inequality? It means that sum of any two sides of a triangle is greater than or equal to the third side, right? But with cosine similarity, that doesn't apply. And the other problem is that it is undefined for zero vectors because the denominator is zero, it is undefined, completely undefined. Then there is Mahalanobis distance, which accounts for correlations. But the problem is it requires a covariance matrix. The sigma here in the middle is the covariance matrix. So it's used for some applications, but not very commonly used. And then there are other distances like the Hamming distance, Jacquard's distance, and Chebyshev's distance. So Hamming distance is the distance between two strings of equal, typically used for strings of equal length. And it is given by the number of positions at which the corresponding symbols are different in the two strings. So it is simple to compute, natural for categorical data, but it is limited to same length sequences, and there's no concept of magnitude really. And there's another distance metric called Jacquard's distance, which is also used in big data quite often, particularly in the LSH algorithm used for approximate nearest neighbors in the vector databases. Jacquard's distance is used. So it is given by this. It is like a Venn diagram with intersections and unions. So it is typically used for set-based problems. And it is sensitive to small sets. So Chebyshev's distance is a special case of this Minkowski distance we saw in the previous slide, right? So Minkowski distance, it's a special case where p is equal to infinity. When p is equal to infinity, all terms in the Minkowski distance become negligible except the maximum absolute difference between the coordinates, right? So that is the Chebyshev's distance formula, right? You can set everything else to zero and only this term will remain. That is the maximum term. So this is typically used for applications where warehouse or path logistics are typically applicable, and when worst case difference matters a lot. So because P is infinite in Minkowski for Chebyshev, it is very sensitive to outliers in single dimension, right? So there are many distances. I just listed some of the most important ones. But let us look at a different kind of distance, totally different kind of distance. So what is the problem with Euclidean distance? The problem is that it assumes that points are on the same hyperplane. So the points must lie on a hyperplane, which is not typically the case. For instance, you take the example of Google Maps, right? Google Maps, when you type in the destination, it gives a distance. And then when you click on start, it gives a different distance. Typically, the distance it gives first is much less than the distance it gives later. I don't know how many of you have thought why, but the reason is that I don't know, but this is my guess. The first distance is a Euclidean distance. It assumes that the 2 points can be connected using a straight line. It assumes that the two cities or the two places are residing on a flat earth that is flat. But that is not true, right? Earth is round. So that is the reason why the distance increases when it comes to reality. So often the distances are not Euclidean. So that's when we extend the distance from hyperplane. Hyperplane is like a plane in multi-dimensions. More than 3 dimensions, it's called a hyperplane. In 3 dimensions, it's called a plane, and in 2 dimensions, it's a straight line, right? So we need to extend distances, the concept of distances to hypersurface. Typically, a lot of surfaces that we discover or that we find in data science are manifolds. So manifold is a topological space um, which is locally Euclidean. Like if you see, each of the small rectangles is Euclidean. It's like a plane, right? It's like a 2-dimensional plane. But globally, the shape could be very complicated. So that is the idea of manifold, right? It's a smooth, typically manifolds are smooth, so it is differentiable everywhere. Just like smooth curves can be differentiated anywhere, smooth surfaces can also be differentiated everywhere. So obviously the Euclidean distance does not apply here, right? For instance, you take the point in the red area and the blue area. So you cannot draw a line between the two. So you have to draw a line along the surface. So such kind of a distance is called a geodesic. So geodesic is commonly a curve representing, in some sense, the shortest path between 2 points on a surface. So many machine learning algorithms like t-SNE, MDS, or isomap, at least some of these use geodesic. They don't use the Euclidean distance. So here's a visualization of the geodesic. It's the shortest distance between 2 points on a manifold surface, honoring the shape, right? For instance, you look at this bug movement honors the shape of the donut. So we measure the movement of the bug honoring the shape of the donut. So that is called, such a distance is called geodesic. So this concept is one of the foundations of geometric deep learning and some machine learning as well. Okay, now back to our algorithms, right? So those are the prerequisites for the to understand the algorithm. But let us look at the algorithm itself. So k-means is the most popular unsupervised machine learning for partitioning data into k disjoint clusters based on features. So the clusters that k-means forms are disjoint. That means there's no point common between clusters. They are all disjoint. And the goal is again to minimize the within cluster distances or variance or dissimilarity. And the dissimilarity or variance is measured by the distance. Typically, the distance is the Euclidean distance, which is the sum of squares. So that is the goal of k-means. So this is the objective function that k-means tries to minimize. So what is what does this represent? It represents the distance. The first thing you need to note is the distance between a point xn and a centroid mu j. So this is the distance of the points in cluster Cj from the centroid of the cluster, the Euclidean distance. I mean, we could use some other distance as well, but for simplicity, I'm using Euclidean distance. And we come up with k such clusters. K is predetermined, it's a hyperparameter. So we sum up these distances for all the k clusters. And we try to minimize this summation, right? So that is the goal of k-means clustering. And this is an NP hard problem. Why? Because suppose there are a billion points. Now each point can belong to a cluster or may not belong to a cluster. So there are 2 power 1 billion ways of arranging the clusters. So brute force method is almost impossible. Even if there are 20 data items in the data set, we are looking at 1 million ways of arranging the clusters. Why? Because there are 20 items. Each can be in the cluster or not be in the cluster. So one cluster can be arranged in 2 power 20 ways, which is 10 power 3 squared, which is 1 million, right? So, and then if you are thinking of k clusters, then it compounds the problem further. So it's an NP-hard problem. So machine learning is typically suitable for NP-hard problems, and that's what we are going to do here. So just like in case of algorithms and data structures, we choose an approximate algorithm, typically a greedy algorithm, for doing the clustering with k-means as well. So it is basically a heuristic. The algorithm itself is a heuristic to optimize this function. It's not a global optima. It's a local optima. So the basic idea is to describe each cluster by its mean value. So xn is a vector representing the nth data point, and mu I is a centroid of the data points in the cluster Cj. And the expression here is the Euclidean distance. So we already talked about it. So k-means is very widely used in segmentation problems, quantization, and hidden structure recognition. So any questions so far? Let me check.
Hi, Vishnu. Thanks so much for taking the break. I can see a couple of questions and comments in the chat box. Do you mind to just quickly review? I'll appreciate that.
Oh, I don't see any questions.
Okay. I have a question. Looks like
Oh, yeah,
does.
got it. Sorry, I got it.
Okay.
Similar genre and our keywords in the description. Oh, so for some reason I was not looking at the chat. Okay, so does this mean clusters change dynamically based on user behaviors? So the means will change with clusters, and if the user behaviors also change, obviously the cluster definitions will also change, the features will change, and the cluster definitions will also change. Therefore, the means will also change. Yeah, it's a very good question. So the idea is that the user behavior changes, then the features change, and if the features change, their position in the vector space changes, and if the positions change, then the clusters change, and if the clusters change, the centroids also change. Yeah, thanks. And yeah, that's the only question I see.
Yeah, right. So JD posted that there is some issue with the sound. Hopefully, JD, you can hear Vishnu well. I can hear Vishnu in my end pretty clear, so I'm not sure.
So let me so I mean the volume wise it's okay, or is there a
Yeah,
problem?
in my end, you're good and you're audible in my end. Yeah.
So let me check the settings. That's a good point. I should have done it. Oh, it is low. So that may be the reason.
Or even improved now. It's even nicer now.
Yeah,
And Jerry said, yeah, seems to better. Yeah. So thank you, Jerry, for come forward and post the message. We appreciate that.
yeah,
It's helpful.
thanks for that. I don't know why Zoom keeps on resetting the microphone.
The volume and this thing. Okay. So Vishnu, thank you so much. I don't believe we have any further question. If anybody like to unmute yourself and ask any question to Vishnu. All right. Okay, I can see a new message there. Oh, okay. So that's not a question. All right.
Okay.
So Vishnu, thank you. And maybe you can restart and continue your talk and we'll be here.
Okay. Thank you.
Yeah, thank you.
So yeah, so this is the objective function. If you are familiar with machine learning, supervised learning, um, every machine learning algorithm typically optimizes an objective function. So for k-means, this is the objective function we optimize. So this mu could be any point, but why do we consider it as a centroid? So why is mu j the centroid? Let us ask a fundamental question. Why do we have to take the distance from the centroid only and not from any other point? So the answer is the intracluster distance is given by this. And this is what we want to minimize, right? We want to minimize the sum of distances from some arbitrary point to all the points in the cluster. So we take the partial derivative of, so we want to find out which point mu is, right? So we want to take the derivative with respect to mu, right? Mu could be any point. So when you take the derivative of the loss function or the objective function that we are trying to minimize with mu, it will be 2 times the sigma, this difference. Because it is minima, we set it to 0. And when you take sigma xn to the right hand side, you get mu j is equal to sigma xn by p, which is a centroid. So which is the formula for the centroid. So that is the reason why we take the distance from the centroid. So p is the number of points in the cluster, right? So this proves that centroid or the mean is the most representative point in the cluster. So that's the reason why we take centroid and not any other point. So, so now let us look at the illustration in a little more detail. So let us consider these data points, right? So there are clearly 2 clusters, one on the left and one on the right. So the only decision to be made is the point in the middle, right? So this point is the one that we are concerned about, the one that I encircled. So which one should it belong to the left or to the right? So you can guess and we'll see whether your guess is right or not. Okay, so yeah, so that is the point we need to decide. So just like before we saw in the animation, we choose 2 centroids randomly. So these are not really centroids because there are no clusters and there are no centroids. These are just pseudocentroids. That's why I call them pseudocentroids. So these red points are randomly chosen. Seeds, you can think them of seeds, think them of as seeds. So they are not real. But in general, centroids are often imaginary and don't appear in the final clustering, just like in the case of triangle, right? The centroid was none of the 3 points of 3 vertices of the triangle. The centroid was in the middle of the triangle. So it was imaginary. It's not a real point in that sense. On the other hand, medoids are real data points. So if you choose one of these data points to represent the cluster, then that is called a medoid, right? Based on the medians. But this one is based on, centroids are based on means, not medians. If it is based on medians, it's called medoid. Okay, so what is the next step? So the next step is we compute the distances from each data point to the first random pseudocentroid. So this is the first random pseudocentroid on the left-hand side. We compute the distances using this formula from each of the data points in both the cluster, in pretty much all the data points. So mu1 is the centroid on the left-hand side. Then we compute the second distance from the second centroid to all other points, right? And we compare these distances. We compare D1 with D2. The first distance is from the first centroid, second distance is from the second centroid. We compare these two distances, and if the point is closer to the second centroid, it will be grouped with the second centroid. And if the points are closer to the first centroid, it will be grouped with the first centroid. So as you can see, for all these blue points, D1 is less than or equal to D2. For all the green points, D2 is less than or equal to D1. And the center point is green for now. Why? Because it seems to be closer to the second centroid than to the first centroid. But it may change. We'll see whether it will change or not. So now that we have some clusters, we will compute the real centroids. How do we compute the real centroids? We apply the formula, right? So the real centroid is computed by taking the mean. So that's what we do. So we compute the centroid for all these points in the blue cluster, all the points in the green cluster, and they become the real centroids. So the centroids actually move inward. So these were the previous centroids, the pseudocentroids. Those pseudocentroids started moving inside. If you have noticed, the centroids were here, and they started moving inside, a little inside the clusters. So they actually moved even more inside. And now we have the real centroids. We compute the distances from both the centroids again, but this time the centroids are real for the clusters. And we compute the distances and compare the distances. And based on the distances, the point in the middle becomes blue. From green, it has turned blue. Why? Because it is closer to the first centroid than the second centroid. So a question, what happens to the objective function with this change to the point in the middle? So this is the objective function. What happens? It reduces. Why? Because the centroids are moving closer and closer to the clusters, right? They're going inside the clusters to become the real centroids. So that's why the distance keeps becoming closer and closer, lesser and lesser. So again, you repeat those steps. You compute the new centroids using the formula, taking the means of the elements. So they move further inside. And you again compute the distances of these two centroids from all the points and compare them. But this time, the points do not change clusters. The colors remain the same, and the centroids remain the same as well because the colors haven't changed. So that means the algorithm converges. So typically the algorithm converges in pretty quick steps, though it might seem like it will take a lot of steps. Typically it converges pretty quickly. So the final clusters after convergence are given by these green and blue points. So now we don't need the centroids any longer. So we can discard the centroids because now we have the final clusters. So all the previous slides now can be seen as an automation. So I implemented this automation, this animation using Manim, a library called Manim to animate. So you can see that, so all the steps that we saw are now animated. So I used the real k-means algorithm and implemented this code, and you will see that the algorithm converged pretty quickly. Probably, if I remember, it was 28 seconds long. So that is the idea. Oh, sorry. It's repeating again. So that is the idea of k-means algorithm, right? So first step is to initialize, randomly select k number of initial centroids, mu1, mu2, mu_k. Then initial selection. One disadvantage of k-means algorithm is that the initial selection drastically impacts the final clustering. You choose different initial seeds, you get entirely different clusters, particularly if the clusters are not well formed. In this case, the clusters were well formed, right? But that is not always the case. So in such cases, the seeds will impact the clustering, final clustering tremendously. So that is the initialization part. Now, what are the steps that we want to repeat? Just 2 steps, like we saw earlier. First is the assignment step. For each data point X, assign to the closest centroid. So we want to minimize this distance from the intra-cluster distance. That is the goal. So based on that, we keep assigning points. And the second step is to update the centroid. So recalculate the centroids. So we keep applying this formula to recalculate the centroid. So we keep doing these 2 steps again and again until what are the stopping conditions? So the centroids no longer move significantly. Typically, epsilon is like very, very small, infinitesimally small. So much so that typically we stop when this is 0. Often this is 0. But we can assign an configurable epsilon just to make sure that it does not loop in infinitely, or it definitely does not loop infinitely, because k-means is proven to converge. It is mathematically proven to converge. So it will converge, but just in case it takes too long, you just set this limit of epsilon, or no change in cluster assignments. So that's it. That is the algorithm. Very simple and easy. One of the easiest algorithms if you are a software professional. Now let us look at a numerical example illustration. So this data set has just 3 features, and we want to come up with 2 clusters. And let us look at the first iteration. The first step is assignment, right? So this is the data set. 3 features, x1, x2, x3. And each of these rows represents an entity, like a sample, could be a student, could be a movie, could be anything. So this is the data set, and we want to group these rows into 2 clusters. Oh, so there's a question on the chat window. I missed the name of the library for the cluster animation. So I used a library called Manim. Manim is popularly used for YouTube videos. MANIM. You can search for it. It's on GitHub also. It is used for it's open source, but I think it's it's popularly used on YouTube. There is a popular series of YouTube videos. I forgot the name. They use that. So so yeah, I use Manim. Hope that answers. Okay, thank you. So the first step is assignment. So we first come up with random centroids. So in this case, the centroids are 0, 0, 0 and 10, 10, 10, randomly, totally randomly. So let us see what happens with these drastically different points from the data. So you start computing the distances from the centroid to each point. For instance, for the first point, I computed a distance for the first point, but you can compute for the remaining also. So for the first point, the centroid is 0, 0, 0, first centroid, and vector is 1, 2, and 3. So 0 minus 1, 0 minus 2, 0 minus 3, which is square root of 14, 3.742 is the first distance. That means the distance of the first point from the first centroid. Similarly, the distance of the first point from the second centroid is 10, 10, 10, and 1, 2, 3 are the are the elements of the vector, first vector. So 10 minus 1 squared, 10 minus 2 squared, and so on. So you get 13.928. So in a similar fashion, you compute the distances for each of the points. So the first point, 3.742 from this, and 13.92 from here. Similarly, the second point, third point, and so on. And then there is a column called cluster, which will be assigned based on the distances. If D1 is less than D2, it will be assigned to cluster 1. And if D2 is less than D1, it will be assigned to cluster 2. That's it. So the first 2 points are in the first cluster. The next 2 points are in the second cluster. Next point is assigned to the first cluster Y. because the D1 is 1.5 and D2 is 10 times that distance, 15. So we assign it to the first cluster, So that's how we do the assignment. So the next step is to update the centroids, recalculate the centroids. So now the clusters are the first, second, and fifth point. So so 1 to 3 is the first point, 1.5, 1.8, 2.5 the second point, and the fifth point is 1.6 and 1. So we take the mean of these three. So 1 plus 1.5 plus 1 by 3, 2 plus 1.8 plus 0.6 by 3, so on and so forth. Similarly, for the second cluster, the centroid is given by these three green points, 5, 8, 9, 8, 8, 7, 9, 11, 12. So we get this as the second centroid. So we again compute the distances from the first centroid and the second centroid. So in the assignment step, we compute so these are the centroids from the first iteration, right? 1.167, 1.467 and all that, 7.33 and all that. So this is the first centroid, second centroid. We compute the distances for each point from each of the centroids. First distance, second distance, right? In a similar fashion like we did earlier. So from iteration to the centroid, so this time the clusters do not change. We still have the first 2 points in the first cluster and the fifth point in the first cluster and the remaining in the second cluster. So the clusters do not change. Therefore, the centroids, if you want, you can still compute the centroids, but they'll remain the same. In the algorithm, we do compute the centroids to make sure that it is less than epsilon. So the difference does not change. The centroids do not change. So therefore, the algorithm converges. And if you plot the points, it looks somewhat like this. So as you can see, there are clearly two clusters, and the algorithm correctly identifies the two clusters. So that is the idea of k-means clustering. So we initialize centroids randomly, we assign points to the nearest centroid, and in a loop, we update the centroids, check for convergence. If it is not converging, we assign the points to the nearest centroid again and again until the convergence is checked, or until the convergence happens. So now the fun part is that this is a specific form of a general algorithm called expectation maximization. So expectation maximization is a probabilistic method often used for fitting mixture models like the Gaussian mixture models. So if there are two Gaussian distributions, so EM is used for identifying the two or more models of Gaussian distributions. So the M step, the maximization step, refers to optimizing an objective function, like maximizing or minimizing. So whenever we update the centroids, we are basically minimizing the distance, right? The distance reduces. The centroids move in such a way that the distance within the clusters reduces, right? Okay, is there something on the chat window? Oh, okay, there's a link posted. Okay, good. So, so we keep expecting and maximizing an objective function, or so maximizing something on the other hand could mean minimizing some other thing, right? There's always a dual in mathematics and optimization problems. Typically, there's a dual formulation of a problem. Maximizing one kind of problem amounts to minimizing some other kind of problem. So but we generally refer to the process as maximization. So maximization in this case actually minimizes the intra-cluster distance, right? That is the maximization step here. And the E step, the expectation step, expects which cluster each point belongs to. So that is the expectation that we are doing. So that is the idea of expectation maximization. The reason I brought up expectation maximization is that EM algorithm is proven to converge, mathematically proven to converge, and k-means is a special case of EM. So therefore, k-means is also guaranteed to converge. So we are sure that the program will end after a finite number of loops. So it will never be an infinite loop. But one thing to remember is that k-means algorithm is a greedy approach. We optimize the distance greedily, right? We minimize the distance greedily. So it's not a global optimum, but a local optimum. So typically the algorithm gets trapped in the local optimum. So that is the reason why for the same data, for different initialization of the centroids, like the different seeds, random seeds, we may get different results. So that is one downside of k-means. So convergence does not imply optimality. Bad seeds can result in bad clusters, or it could also result in slow convergence. The other problem with k-means is we don't know the value of k in advance. How do we determine the value of k? So how do we determine the value of k? How many clusters? So typically we need to visualize the data in low dimensions. So even if the dimensions are 1,000 or 1,000,000, we can visualize them as two-dimensional vectors using techniques that I described in this video. So if you're interested, you can watch this video. I don't think it will play. Okay, anyway. So there's a video, you can search YouTube and you'll find that video. So you can watch it on how to minimize or represent high dimensional data in lower dimensions. The other way to determine k is, so the reason you should do that, representing in the lower dimension is, when you represent in 2 dimensions, it might look like this. Then you know for sure that there are only 2 clusters. Or it might look like look like this. Then you can clearly see that there are 4 clusters. So that is the reason why it is good to represent data in lower dimensions, right? So that is one way of finding the value of k. The other way of finding the value of k is come up with this kind of a plot. So on the y-axis, you plot. So the goal of our algorithm is to minimize the number of the objective function. So the y value must be as minimum as possible, but you can pretty much make it 0. When will it go down to 0? Does anyone know? Can anyone take a guess when it can go down to 0? So it will go down to 0 when each point is a cluster. So there's only one point in the cluster, then the point itself is the centroid. And when the point itself is the centroid, the value is 0. So you pretty much get the y value to 0, go down to 0, when the number of clusters is equal to the number of points. But that is not our intention. So we don't want that. We want as minimum clusters as possible and as minimum distance as possible. Therefore, we will choose the elbow of this graph. So this is like the elbow of the graph, right? The value 3 for which the value of k is 3. So this is the elbow of the graph, and this is what we are going to go with. So for this problem, so we compute for various values of k, number of clusters, we compute the within cluster sum of squares, WCSS. which is the objective function. And as you can see, for when there is just one cluster, all the points in one cluster, the distance is way too high, 19,953. For two clusters, it halves, drastically halves, 9,400, so on and so forth. For oh, sorry, this is oh yeah, that's right. So for three clusters, it goes down to 2110. So this is the point that we choose. We choose k is equal to 3. So we, for this data set, for the data set for which this is the plot, we come up with three clusters. So this is the elbow. Now let us look at the computational complexity of k-means, right? So what are the computationally intensive steps in the algorithm is what we are going to look at, right? So the computational intensive steps. So the algorithm keeps looping for I number of times until convergence. Suppose it takes I number of iterations to convert for the algorithm to converge. So I is definitely a loop variable. Then the other loop variable is the k, right? The number of clusters in each. Sorry, the number of clusters. I made a mistake here. So it is just the number of clusters. K is the number of clusters, and n is the number of data points to compute distance of each point from k centroids. So for each centroid, we need to compute the distance from each of the data points, right? If you remember. And if there are n data points, so we loop on n. And to compute individual distances, we loop on d, the dimension, right? Because if you remember the Euclidean distance, for each dimension, we compute the difference, right? So that is the fourth loop variable. So if you remember the Euclidean distance, we loop on each dimension. If there are three dimensions, there are three terms. So we loop on the dimension also. So that's it. Therefore, the time complexity of k-means is of the order of n into k into d into I. The good thing is it is linear in all factors. The factors are n, k, d, I, and it is linear in all these factors. So that is the computational complexity. It is not too bad. But the disadvantage is that k-means can draw only linear boundaries. For instance, if this is the original data set, so moon crescents, there are two moon, the data set when arranged, when plotted, looks like moon crescents, two moon crescents. So we expect the clusters to be like this, but k-means forms these kind of clusters. They draws basically linear boundaries like this, which is not what is desired. So that is the problem. Similarly, so these kind of circles cannot be identified by k-means. It can only detect clusters that are linearly separable like this. So that is another big disadvantage of k-means. So that's why we look for other algorithms. So the next algorithm we are going to talk about is the DBSCAN algorithm, right? So DBSCAN stands for density-based spatial clustering of applications with noise. So it was published in 1996 in the KDD conference, ACM KDD conference. The algorithm is abbreviated as DBSCAN. It's a very powerful clustering algorithm particularly for complex data and data with noise. So what are the key insights of DBSCAN? First is that the cluster, so it clusters data points that are closely packed, so based on density, right? So the notion here is density, not that of the center, but that of density. So points that are in low density regions are flagged as noise. right? So the simple algorithm is based on two hyperparameters to define what we call as dense. So how do we define density? It is based on epsilon. Epsilon is the maximum distance between 2 points for them to be considered as neighbors. So if you go back to the example of homes, so we want to um, determine the radius of the neighborhood to call a community dense, to call it a community basically. We call it a community only when the neighborhood is dense, right? So the radius of this area, neighborhood, is the first hyperparameter, which is called epsilon. So that is the first hyperparameter. And the second hyperparameter is the min points, minimum number of points required to form a dense region within a radius epsilon, right? Going back to the homes analogy, you cannot draw a very big radius and call it a dense region, right? So it is also defined by the minimum points as well. So both together will control the neighborhood, epsilon and min points. So these are the two controlling hyperparameters for to identify dense regions. So many applications of DBSCAN, particularly wherever there is noise, DBSCAN is very well applicable, like in case of climate data. So climate data is typically noisy, right? Like particularly in the recent times, weather has been going up and down pretty much everywhere in the, at least in US probably. So it is very noisy. So for such applications, DBSCAN is a great algorithm. And also for geospatial data, so identifying regions with high population density. So is a good application. And then anomaly detection. So detecting fraud or irregular patterns in data. It is so heavily used for anomaly detection that this is a chosen pre-processing step for many machine learning algorithms. So before applying a classification algorithm, you pre-process the data to remove noise using DBSCAN. So anomaly detection and removal is a great application. And then image segmentation, identifying regions of interest in images. So DBSCAN can form clusters. The one big advantage of DBSCAN is it overcomes the limitations of k-means. So k-means would not be able to form these kind of circular clusters, this half crescent moon clusters, and things like that, right? But DBSCAN can form clusters of varied shapes. So it can form clusters like this. It can form clusters like this one on the right-hand side, and sizes also. It's not just shapes, but also sizes, varied shapes and sizes. So let us look at how DBSCAN works, right? Again, I'll go back to the same page, which I really liked. So it is a very cool demo. I will use smiley faces this time. So as you can see, there are some dense regions in the face itself. So the eyes, the mouth, the face cut, that's all dense. So let us see how epsilon does it. So we choose epsilon as 1 and min points as 4, and then see how DBSCAN works. So as you can see, it keeps drawing circles, right? It keeps drawing circles. Why does it draw circles? And what is the radius of the circle? It is epsilon, right? Because remember, we determine neighborhoods based on epsilon radius. So it went on drawing red circles to identify the red points until it hit a break. So the distance apparently is more than 1. The distance between this red point and white point was more than 1, so it broke there. Then it started going back to the previous place where it started, and then drew blue circles and came up with this blue cluster. Similarly, the green cluster, yellow cluster, and the gray cluster. So that's it. That is the algorithm that we are going to talk about now. So the algorithm repeatedly identifies dense neighborhoods, right? So, so for that, we need to define, we need to make some definitions, provide some definitions, right? So the first definition is that of core, border, and noise points. So what are core, border, and noise points? So they are demonstrated on the right-hand side. The blue points are the core points. There are only 2 core points here. The green points are the border points, and the red points are the noise points. There are a lot of noise points. So these definitions are with respect to an epsilon distance of 1.7. That means the radius, this arrow, red arrow, is no greater than 1.7 based on the x and y axis. And the min points, the number of points within the radius, should be at least 5. Only then it will be called a neighborhood. That is why green point wasn't a core point. Why is it not a core point? Because there are not 5 points in the radius of 1.7 from this green point. So that is the idea. So core point are points with at least min points neighbors within epsilon and will be included in a cluster. So the core points are the ones that get into the cluster. Border points are also get into the cluster, and these are the points that are reachable from a core point, but do not have enough neighbors to be core points themselves. So there are not enough min points. There are not enough points around the border points to make a neighborhood. So then they are called border points, but they are within the neighborhood of another point. So that is why they are called border points. And then the remaining are noise points. Points that are neither core nor border points are often considered outliers or noise. So that's it with these 3 definitions. We can come up with some fundamental concepts of clustering. So, but you have to remember one thing, the definitions will change. The points will change based on the values of epsilon and min points. If you reduce min points to 2, then this green point here will also be a core point, right? And if you increase the epsilon to maybe, how much is this? -8, is it? -8 to -2 is 6. If you increase the epsilon to 7, for instance, then a whole lot of points will be core points. So it is very sensitive. The algorithm is very sensitive to epsilon and min points. So more definitions based on these points, right? These ideas. So the next definition we want to consider is that of directly density reachable points. So a point P is directly density reachable from point Q. Again, everything is with respect to epsilon and min points, because everything will change if you change epsilon and min points. So all the definitions are with respect to epsilon and min points. So there are 2 conditions to be met. First condition is that P is within the epsilon neighborhood of Q. That means the distance between P and Q should be less than or equal to epsilon. And the second condition is that Q is a core point. So when do you call a point a core point? All points P dash in D, the number of all points P dash in a neighborhood D such that the distance between Q and P dash is less than or equal to epsilon must be greater than or equal to min points. This is a mathematical way of explaining what we mentioned in English in the previous slide. So the distance must be less than epsilon. And such points should be greater than or equal to min points for Q to be a core point, right? So that is the idea. So, so as you can see, the blue ones are the directly density reachable points. Why are they directly density reachable points? Remember, they are not all core points. For instance, this is not a core point because there's only 2 points, not 3 points to satisfy the core point definition, right? So this is just a border point. This blue point is a border point, but it is still directly density reachable. Why? Because it is within the neighborhood of a core point, right? This is a core point. Why? Because there are 3 points here. This is a core point. There are 3 points here. Similarly, all the other 2 blue points are core points. So this is the only blue point which is not a core point, but it is still directly density reachable point because it is within the epsilon distance, within the neighborhood of a core point. Now, one important observation is directly density reachability is not symmetric. So this point is directly density reachable from this point. But this point is not directly density reachable from this point. Why? Because this is not a core point. Only one of them is core point. So that is the reason why it is not symmetric. So it's a one-way relationship. It's not a two-way relationship. So the next idea is that of a density reachable point. So when is a point density reachable point from another point? When there is a chain of points that are directly density reachable, starting from Q and ending at P. So that implies P is a density reachable from Q with respect to epsilon and min points. All the definitions are with respect to epsilon and min points. So what does that imply? So is P a core point? Min points is 7, obviously not, right? So Q 1, 2, 3, 4, 5. There are only 5 points, maybe 6 points. So it is not a core point. But Q is a core point. Q needs to be a core point. So Q, P1, P2 must be core points. So once again, this is also not symmetric. It's a unidirectional relationship. It's one directional relationship. For the same reason that direct density reachability is not a symmetric relationship, right? So that is the second concept, density reachable points. Q is density reachable from P. So the third concept is density connected. So P and Q are said to be density connected, of course, with respect to epsilon and min points, if there exists a point V such that P is directly density reachable from V, right? So there should be a point V such that P is directly density reachable from V and Q is also directly density reachable from V. So there should be a connecting point V such that V is a core point and P and Q are directly density reachable from V. So that is the idea. So in this case, these 4 points, the 3 blue points and 1 red point, are all directly density reachable points. Sorry, density connected points. So red point is not a core point. The blue points are core points, because they have 3 points in their neighborhood, but this red point does not have 3 points in the neighborhood with radius 1. But it is still density connected with the with the blue points. Why? Because there's a common core point between any other points and this red point. So that's the reason why it is density connected to the 3 points, 3 core points. So now the good thing is density connectedness is symmetric. So if P and Q are density connected, then Q and P are also density connected. Why? Because neither P nor Q has to be a core point. As long as they have a point V, which is a core point, connecting them in the neighborhood of both the points, we are good. So those are the 3 definitions. So density connectedness is key to how DBSCAN forms clusters. By now you would have realized that. So by using the concept of density reachability and density connectedness, the algorithm connects points that are spatially close and have sufficient density to form clusters. And the algorithm flags points that do not meet this criteria as noise. So now we are ready to design the algorithm. So let us look at the algorithm. So the first step in the algorithm is initialization, right? So the input is a set of data points along with 2 key parameters. What are the parameters? The parameters are epsilon. These are hyperparameters. The maximum radius of the neighborhood around a point, and min points, which is the minimum number of points required to form a dense region cluster. And what is the output? The output is a set of clusters with some points possibly marked as noise. So we identify clusters and noise. And for each data point, DBSCAN classifies it into one of the 3 categories based on the definition. So if a point has at least min points, including itself within its epsilon neighborhood, it's called a core point. So it classifies it as a core point. And if a point has fewer than min points within its epsilon neighborhood, but is within the epsilon neighborhood of a core point, then the algorithm classifies it as a border point. And a point that is neither a core point nor a border point is flagged as a noise point. Now, the next step is forming clusters. So start from any point. If the point is a core point, a new cluster is started, and all points in its epsilon neighborhood are added to the cluster. So then the idea of density connectedness comes into picture. The density connectedness between core points is what allows a cluster to expand. So if any of the neighboring points are core points themselves, their epsilon neighborhoods are recursively processed. So if the core points are density connected, then so that is if they can reach each other through chains of direct density reachability, the algorithm merges them as clusters. So for each core point, epsilon neighborhood recursively expand the cluster by checking whether the neighboring points are core points or border points. So we are basically combining those small circles into clusters, the neighborhoods in small circles into clusters based on the density connectedness. Then border points are assigned to the cluster of the core point that expanded them. So there are multiple ways of dealing with border points. This is one way of dealing with border points. The other way of dealing with border points is based on the majority. But anyway, let us look at this way. So the border points, remember, border points could be border points to multiple clusters, more than one cluster, right? They could be in the neighborhood of multiple clusters. So they are assigned to the cluster of the core point that expanded them. So that is the simplest way to deal with it. So once it is assigned, that's it, you forget it. That is what this point is saying. Points that are neither core points nor border points are labeled as noise. And when does this stop? The algorithm stops when all points have been processed. So either assigned to a cluster or marked as noise. So that's when the algorithm stops. But when does the cluster stop? When the cluster stops when it encounters a border point, right? The moment it encounters a border point, it stops forming cluster. It goes on to start a different cluster. So here's another illustration of clustering algorithm, a DBSCAN clustering algorithm. So here you form 3 clusters. So the red ones are the border points. And the gray ones are the noise points with respect to epsilon and min points 3. So the good thing is, or may not be so good thing, the problem is that the complexity, the computational complexity is n log n, which is not, it is somewhat okay, but it can get really nasty with big data. When there are billions of points, then it can become really nasty. So any questions on the chat window? No, nothing so far. Okay. So yeah, that is a computational complexity. But the good thing is it is noise resistant clustering. So like I mentioned, DBSCAN in fact is used often for pre-processing, for removing noise from datasets. So DBSCAN identifies points as noise. It need not even form these clusters because identification of points as noise is one of the first steps that DBSCAN does. As soon as it identifies noise, you can just remove them from the dataset in the pre-processing step. So you know that data science, typically 70% of the time goes away in pre-processing, identifying noise, cleaning the data set and all that stuff. So DBSCAN helps in that. But there is a disadvantage. What is the disadvantage? DBSCAN is heavily sensitive, highly sensitive to hyperparameters, and it is hard to choose the right ones. So what are the 2 hyperparameters? Epsilon and min points, right? So if you see here, this is from a book by, I found this figure in the open domain, public domain, with a CC by copyright. So I thought, but I know that this figure is from the textbook. So I just also attributed the figure to the textbook. And by the way, this is a good textbook if you want to read. So DBSCAN forms these kind of clusters and these kind of noise points for epsilon 0.5. Sorry, yeah, epsilon value of 0.5. You get nice clusters like this. But you change the epsilon to 0.4, just a small difference in epsilon, it completely changes the clusters. Now you see completely different clusters, right? This circle is totally broken down, and you have many clusters now. That is the effect of epsilon. Now, if you look at the effect of min points, so with min points 4, again, the second example is also based on epsilon. So in the second example, for min points is equal to 4 and epsilon at 5, it does nice clusters. But you reduce it slightly to 3.5, then it changes the clustering completely. And if it is 3, again, entirely different clustering. 0.5 difference makes such a big difference in the clusters. So which is not a good thing, right? Because particularly when it is difficult to choose the hyperparameters efficiently. So that is the challenge with DBSCAN. So next is the hierarchical clustering, which is the most natural way of clustering and coming up with taxonomies, right? So what are the key insights of hierarchical clustering? Any questions? Let me check. So there are no questions. Let me check one other thing. Yeah, there are no questions.
No, there is no question, Vishnu. I'm also doing follow-up. Thank you.
Okay. Okay, good. Thanks. So hierarchical clustering organizes data into a hierarchy of nested clusters, like the name indicates. It is typically visualized as a dendrogram. You would have come across dendrograms in botany and zoology and those kind of places. So it is widely used in biological sciences for gene clustering and for taxonomy creation, such as in web catalogs. So wherever you need an order to be placed into the clusters, like in taxonomies, you use hierarchical clustering. The good thing is there is no need to predefine the number of clusters. It is quite flexible. Any number of clusters can be obtained by cutting the dendrogram at the desired level. So you can come up with 2 clusters, 3 clusters, any number of clusters. So that is the biggest advantage. But the downside is that the complexity, the computational complexity is quadratic. So it is computationally intensive for large data sets. If there are like millions of points, then it's going to choke. The algorithm is going to choke. So there are 2 ways of doing hierarchical clustering. So the first way is bottom up, which is called agglomerative. So we start with each point as its own cluster. So each point becomes a cluster. And we iteratively merge the closest clusters until one cluster remains, until one single cluster remains. So that is agglomerative. And divisive is top down. We start with one all-inclusive cluster. That means all the data points are in a single cluster. And we recursively split clusters into smaller groups based on dissimilarity. So once again, this entire clustering is based on the notion of distance, right? You can use different distance metrics. Typically, Euclidean distance is used, but we have talked about so many other distances also. So let us look for look at a toy data set. This toy data set has just 5 data items. Sorry, so how many? 31, I think. I gave 31. So all these plots are generated by the programs that I created. So in fact, for hierarchical clustering, I created the slides today morning. So I think I gave 31 points, and for 5 clusters. And so the cluster standard deviation, I set it to 3. And the way to measure the distance between the points, I used watt. So this is a hyperparameter. We'll talk about it in a little while. But just for now, keep in mind that there's a method, different ways of measuring the distance, not the distance metrics, but using the distance metrics also, there are different ways of measuring the distance. So the method that I use for this, coming up with this dendrogram, is called Ward's method. So dendrogram, like you remember from your biology classes, is a binary tree. So the idea is that the length of the branch determines the dissimilarity between data points. So the x-axis are the samples, and the y-axis is the distance between the samples. So the longer the branches connecting the leaves to the clusters, the greater the dissimilarity, right? So so this is the scatter plot of the 31 points that I plotted. Once again, let me check. It is 31, right? Yeah, I remember it as 31. Anyway, So the scatter plot shows up like this. So there are no clear clusters. I deliberately did that because I gave a large standard deviation, 3. So I deliberately wanted to see how agglomerative clustering performs with this kind of a standard deviation. There are no clear clusters. Still, the clustering worked, right? But there are some outliers in the data set itself, right? You can think of them as outliers. For instance, this is an outlier, the one at the top, or this one is an outlier. These are at the extremes. So these are all outliers. You can think of them as outliers. So point 30 is an outlier. From looking at the dendrogram, I could say that point 30 is the outlier. Why is that? How could you say that it's an outlier? The reason is because so point number 30 is here, right? And it is the farthest from the length of the branch is the longest across all other points, right? So 30 does not is not similar to any other point. The closest similarity of point 30 is with this whole cluster, right? And it is the longest branch. So that's why I could say that it's an outlier. So that is the idea of constructing a dendrogram from these kind of data points. These are all vectors. Remember feature vectors? So these are all points with dimensions, with magnitude and direction. Right? So we converted this kind of a scatter plot in the vector space into this kind of a dendrogram. So we'll look at the algorithm in detail, but this is the idea. So as you can see, these clusters can possibly correspond to meaningful taxonomies, right? So this small cluster here, this cluster here could be, this orange cluster could correspond to some bacteria or something like that. And this green cluster to the right could correspond to another bacteria. So things like that. And within the bacteria, there could be some subclasses, right? So that is the idea of dendrogram. So that is the reason why often in genetics and biology, clustering, the most popularly used clustering mechanism is hierarchical clustering. So you can construct a heat map. There's a library called Seaborn, Python library called Seaborn. So this is constructed using Seaborn. I think so because I got this in the public domain, CC by copyright. So this might be from some paper, but I could not locate the paper. I searched Google, but I could not locate the paper. I found many similar figures, but not exactly this one. So I'm exactly not sure what's happening, but I can guess. So the y-axis is the columns. Let us look at the columns first because they are smaller. The columns probably represent samples, and the rows probably represent, they do represent genes actually. The genes are all labeled here on the y-axis. So the y-axis is the genes and the x-axis are the samples possibly. And the colors, what are all these colors? The colors indicate the data values shown in the legend. So for instance, red is almost 2. The value 2 is represented by red and the value minus 1.5 is represented by dark blue. So between red and blue, there are many colors for representing various values. So you can answer a lot of questions from this heat map, right? For instance, if I ask you, which 2 samples are the most similar? How can you say? So the other good thing is these samples and the genes are connected using a dendrogram as well, right? And dendrogram tells you which 2 columns or which 2 rows are similar. So for instance, the leftmost 2 columns have the least length of the branch. The height of the branch is the least for the left two rows, left two columns. So that's why T1B and T1A are the most similar in terms of samples. Whereas genes, let us now look at genes. Which two genes are the most similar? So if you look at the genes for the smallest branches, so these two rows have the smallest branch length. The branch is hardly visible here, right? So probably these two are the most similar. So the gene number is 8694 and 14672. So these are the two closest looking genes. So why do we compare genes and do all this? Because it will give a lot of insights into the way viruses, for instance, progress, and you can discover medications, vaccines, and so on and so forth. So the good thing is the clustering algorithm, which came up with these dendrograms, considers the entire row or column, not just single cells for clustering, right? So that is a good thing. So now let us look at the algorithm. Now that you have the intuition and the motivation to study hierarchical clustering, let us look at the various algorithms. So the first is the divisive clustering algorithm. So what is a divisive clustering algorithm? Start with all points in one cluster, recursively split clusters based on similarity, dissimilarity or similarity. Then the sequence of splits can be shown using a dendrogram, right? So that is the idea. Now, the good thing about dendrograms is horizontal cuts to the dendrogram define the number of clusters desired. And but the thing about divisive clustering is it is less commonly used due to higher computational demands. The computational demands are much higher, so therefore we rarely use divisive algorithm. So I need to explain this point. Horizontal cuts to the dendrogram define number of clusters. So let us take this dendrogram here. Now suppose we want to come up with two clusters. We can cut the dendrogram here, right at the top. You cut it here horizontally, then you end up in the green cluster and the orange cluster. So that's how you come up with two clusters. If you want to come up with 4 clusters, then cut the dendrogram here, right? Cut 4 branches here using a horizontal line. You will get 4 dendrograms. You want 3 dendrograms, you cut slightly above this yellow line, but below the green horizontal line, you get 3 dendrograms. So that is the idea. If you can come up with any number of clusters as you want, right? So that is the idea. That is a powerful idea of another powerful idea with hierarchical clustering. Okay, so that is divisive clustering. Now let us look at the more commonly used algorithm, which is the agglomerative clustering algorithm. So the idea is to compute the distance matrix between data points first. So you compute all the possible distances. If there are 1,000, how many distances are possible? 1,000 times 1,000 distances, right? Or maybe half of it, because distance is symmetric, right? Then, so initially the distance will be 0 because each point is a cluster. Then in a loop, we repeat 2 things. We merge the 2 closest clusters. I think I should have swapped the first 2 bullets. I think I got mixed up. Anyway, so merge the 2 closest clusters is the first step, and the second step is update the distance matrix. Right? So we keep doing these 2 steps. Merge the 2 closest clusters and update the distance matrix. The distance matrix obviously keeps changing based on the distance from the 2 closest clusters. So initially, the distance is the distance between the points. But in the next round, it will be the distance between the clusters, two closest clusters, right? So we stop when only one cluster is remaining. So what are the distance metrics? What are some of the ways to measure distance? So one way of measuring the distance is called single linkage. So this is the minimum possible distance between two clusters. We'll see what this means, but for now, just remember these names. So the distance metrics can be single linkage, which will be minimum, complete linkage, which will be maximum, or it could be average linkage, or it could be distance between the centroids of the clusters, or it could be using a specialized algorithm like the Watts method, right? Or it could be something else also. So these are the most popular ones, so I listed them all, but there could be more, right? So those are the different ways of measuring clusters, distance between clusters. So what does, say, distance between centroids mean? So it simply means you calculate the centroids of the 2 or 3 or 4 clusters, and then distance between the clusters is the distance between those centroids, right? So that is the easiest one. But what is single linkage? The names are a bit sophisticated, fancy, but the idea is very simple. Single linkage simply means the minimum distance between the two clusters. So find the points closest to each other from the two clusters and find the distance between those 2 points. That is the minimum, that is the single linkage. So A and B are 2 clusters. Find the points which are the closest across from the clusters. The distance between them is the single linkage. Now complete linkage is the opposite. Find the farthest points across from the 2 clusters, and the distance between these two points is the maximum distance, also called as complete linkage. So these terms are coming from graph theory basically. We don't have to bother about the names, but that is the simple idea. So that's the 2 ways of computing clusters. So why do we cover all these different ways of computing distances between clusters? Because each way of finding the distance makes a huge difference to the clusters. We'll see how. Now, average linkage is compute all the possible distances between the clusters. So there are 3 points in the first cluster A, 3 points in the second cluster B. So there are 9 possible distances. So compute all the 9 points. Compute all the 9 points, 9 distances, 9 possible distances, and take the average of all the 9 distances. That is your average linkage distance. So that is the third way of finding distance between clusters. Centroid distance, you already know. You find the centroids, which are imaginary points in the clusters, and find the distance between the centroids. So that's the fourth way. Now, Watts method is a more involved method. So the first step, it has multiple steps. The first step is, of course, to find the centroids of the clusters. So here, centroid for the cluster A and centroid for the cluster B are shown here. Then you calculate the within cluster sum of squares, just like in case of k-means, right? You compute the distance from each point in the cluster to its centroid and find the total sum of distance for cluster A. Do the same thing for cluster B and find the total error sum of squares. So this is like the objective function that we try to minimize. So ESSA plus ESSB. ESS stands for error sum of squares. So find the distance for A, find the distance for B. So variance, error sum of squares, distance, Euclidean distance, they all pretty much are similar because they are all squares of differences. So calculate the error for hypothetical merged cluster. So suppose you merge A and B. So what's going to happen? Will it reduce the, it'll of course increase the this sum, right? Sum of the cluster, intra-cluster distance. But so first step is first find the ESS for the cluster when both the clusters are merged. So find the ESS for A union B, right? So that is the third step. And then calculate the Watt's distance. So this is what makes the difference. So Watt's criterion says that you compute the intra-cluster distance when the two clusters are merged and subtract the individual ESS, the sum of the individual ESS from this combined ESS and see if it increases, right? So you measure the increase. If it, and then try to minimize this. So that is the Watt's criteria. So this is the third, this is the fourth way of finding the distance. So let us take a numerical example and illustrate. So we have just 5 points, data points, with 2 features each, A, B, C, D, and E. And you find the Euclidean distance between the points. So this matrix, the proximity matrix is the distance matrix. These fields are all distances, Euclidean distances from A and A, it is 0, right? So the diagonal will all be 0. And it is a symmetric matrix because distance between A and B and B and A is the same. So it's a symmetric matrix. And so when you plot these points in a scatter plot, they look almost like lined up on a straight line. But when you plot them as dendrograms, you can actually form clusters like this. So if you use complete linkage, so okay, let us look at the proximity matrix more closely. So which 2 points will get combined together first? How do you know? So you decide that, you make the decision based on the values in this table, right? Based on the values in this table, you make the decision. So you look at all the values in the table and find the minimum value in the table. So in this case, the minimum value is between A and B, right? 2.82 something. Actually, the distance between A and B and C are the same, right? C and B and A and B, 2.828427. So you could choose either. So I think these algorithms are choosing the implementation that I used are choosing A and B. So A and B is joined first together. So you'll find A and B joined together for all the dendrograms using different approaches. There's no difference. Complete linkage, group average. In fact, group average and complete linkage show hardly any difference for these points. For these points, group average or complete linkage are the same. But we'll see later for different data sets where group average will greatly differ from complete linkage. But if you look at single linkage and Watt's method, the clusters are entirely different, right? If you look at the previous ones, okay, Watt's method is similar to group average and complete linkage, but single linkage is totally different. Why? Because remember A and B and B and C, or A and C for that matter. No, A A and C and B and A and B and B and C, the distance is the same. So that's why it's plotted with equal branch lengths. But you get the idea. You can come up with different dendrograms based on the linkage that you follow. So if you look at the proximity matrix as a heat map, this is called a heat map, right? So it will look quite different. Yellow being the most distant and blue, dark blue being the least distance. You can see a whole pattern, right? So that is the idea. You keep on generating this kind of proximity matrix. The matrix shown on the slide is only for points, but you have to generate this proximity matrix for each step, right? So that is why it is computationally very intensive. So for this simple five-point data set, there's not much of a difference in the dendrograms. But if you consider different data sets, like, by the way, these are all two-dimensional data sets. And if you look at what each of these linkage methods does for these data sets, you will see a whole diversity, right? So single linkage finds the circles properly. Average linkage, again, is linear. It's almost linear. It does not find the circles. Complete linkage is also linear. Word linkage also does not find the circles. Even for the moon crescent, the same thing happens. For other data sets, something else happens, right? So as you can see, even the average linkage, complete linkage, and word linkage are different, right? The clustering obtained is similar, but quite different as well. It is similar in some ways, but quite different in other ways. So like this one, it's quite different. So that is the idea of average of using different linkages. So for different data sets, you will find that one or two of the linkage methods work the best. So for instance, and also they differ in terms of the speed, right? Single linkage is basically just computing one distance, so it is standouts for its speed. And it does a good job with non-globular data also. Even when the data set is not circular, it does a reasonably good job, like in this case, right? But it is not all that good when there is noise involved. Like in this third from the top data set, you'll find a lot of noise points. So it did not do well. It pretty much grouped everything into a single cluster, right? So it does not do well on the noise data sets. On the other hand, average and complete linkage can separate globular clusters. Like this is a globular cluster. It can separate separate globular clusters if required. But its performance, their performance of average linkage and complete linkage can vary with the data set. So word linkage is found to be the best for noisy data sets. So if you are using hierarchical classification and noisy data set, word linkage works the best. If you are not using hierarchical, then DBSCAN works the best. So this is a comparison of a lot of approaches to clustering. As you can see, there are many more algorithms, but we covered the important approaches. So the other ones are kind of hybrid approaches and some more improvements and things like that. So there are many approaches to clustering, and each approach comes up with a different clustering mechanism. So that is the idea of studying multiple unsupervised clustering algorithm. Just like you study multiple supervised algorithms, you study multiple clustering algorithms, right? So another point, so these sources are from scikit-learn website. So apparently they tune the hyperparameters to produce the best clustering results, or at least very good clustering results. So that means it's not really realistic. And the other thing is these are all two-dimensional data sets. So these examples give some intuition about the algorithms, but this intuition may not apply to high dimensional data. When the dimensions are more than 2 and particularly thousands, then this intuition may not really apply. But it shows you the wide spectrum of possibilities with clustering algorithms. Now, as we have seen, different clustering methods produce different clusters, right? We have seen different clusters being produced. So that is a challenge in itself. For instance, so the data set, original data points are shown in this red circle. You could come up with this kind of clustering for 4 clusters, or you could come up with some other ways of clustering, right? So there could be multiple ways of clustering the same data. So how do we know which cluster arrangement is the best? So the answer is no evaluation metric is perfect. We need to depend on heuristics, right? So for evaluating clusters, of course, we cannot completely leave it up in the air. We need some kind of math and science to understand the performance of the clustering algorithms. So the metrics are often based on sum of intra-cluster distances. But eventually what matters is the impact of clustering on business and application needs. So the final authority in evaluation is the human user, right? So that is the bottom line. The human user, like for instance, if you are doing clustering for your senior vice president of marketing, then whether your clustering is effective or not, only your SVP can say, right? Based on the return on investment and things like that. So that is the idea. But one majorly considered method of evaluating clusters is called the Szilard score to evaluate the quality of clustering. So Szilard score is a mathematical formula. It's a simple formula of using 2 distances. So the first distance is A, which is our familiar distance between a point. So by the way, Szilard score is for a point. And so the score uses 2 distances, A and B. A is the average distance between a point and all other points in its own cluster. So that is the intra-cluster distance. It is quite familiar because we considered this case for A is equal to the mean, the centroid, right? But only thing is in this case, A is not the centroid, but you take any one point in the cluster, find the average distance between that point and all other points in its own cluster. So that is A. And B is the average distance between a point and all the points in the nearest cluster it does not belong to. So this is representative of the inter-cluster distance. So you subtract, obviously B should be more than A, otherwise there's no point in clustering, right? So B will be more than A. So the Szilard score will always be positive. So when is this maximum? So one second, it can be negative also, but negative case is really rare, right? Negative case is very rare. So when is this maximum? So S is given by B minus A divided by maximum of A and B. So it is maximum. Okay, let us consider the easier answer, right? Yeah, when is it maximum? So it is maximum when A is 0, right? When the average distance between a point and all other points in its own cluster is 0, then it is maximum. Silhouette score is maximum. So when does that happen? When does the average distance between a point and all other points in its own cluster be 0? When the point is a cluster in itself, right? So that's the maximum case. But in general, B must be as high as possible and A must be as low as possible. So that is the idea with which we started. If it is the other way around, then it is not a good clustering at all. So, so that is the idea. So it is often used for selecting the optimal number of clusters. So remember, finding K in K-means is a problem in itself. We use the elbow method, but that is not always efficient or optimal. So sometimes a silhouette score is used for choosing K. So basically we choose K with the highest average silhouette score, right? So that is how silhouette score can be used for finding the optimal clusters, number of clusters. Now, when is S close to 1? When the data point is well clustered, far from other clusters. So that means the point is well seated in a cluster, then it will be close to 1. It will be close to 0 when the point is on the border of the clusters, unclear which cluster it belongs to, right? Because in such cases, B will probably, I mean, A will be the highest, and it's not sitting very close in the cluster. S will be close to -1 and if the data point is probably in the wrong cluster. So that is the idea. So the problem with silhouette score is that it is sensitive to the shape of clusters and it may not perform well for non-convex clusters. See, K-means is a convex optimization solution, right? It forms convex, the method is convex. So it's not good for non-convex clusters. Just like that, even silhouette score is not, may not perform well for non-convex clusters. So that ends my session on clustering. So please feel free to stay in touch. I am on the internet quite widely, on social media, Twitter, Facebook, everywhere. And I'm open to any questions.
All right. So thank you so much, Dr. Pandalia. We appreciate your time and for presenting this wonderful tutorial. Just I'd like to put a note that this session also hosted and supported by School of Physics and Computer Science, Wilfrid Laurier University.
Oh.
All right, so let me look at, all right, so we have few comments. Thank you so much, Angelina, for your appreciation. We enjoy your presence and your support for this session. All right, so I can see some folks are still available. It's already in our Eastern time. It's 5 minutes after 9 p.m., so it's quite late. So if you have any question, please come forward, unmute yourself, and please ask your question. If not, then we are going to conclude this session pretty soon, maybe in 5 minutes. All right. So, Dr. Vishnu Pandalia, I don't believe no one has any question, and thank you so much again for presenting this wonderful tutorial on machine learning, especially on clustering algorithms. So we enjoyed this session, and we'll be in touch with you. And thanks for posting your social media links. So if anyone has any queries comes after this session, they certainly can contact with you. And again, we appreciate your time. So have a good night and we'll see you sometime again in some other events. And again, we appreciate your time. Thank you.
Thanks,
So,
Aman.
Angelina, if your microphone works, please feel free to tell us something if you want. Okay. Yeah, it looks like your microphone is still not functioning. That's okay. We appreciate your presence and your support. All right. So we are concluding the session. Everybody have a good night. Take care. Bye for now.
Thanks, everyone. Thank you, Zaman.
Thank you.
Thanks.